Okay, good morning everybody. I'm going to continue in the line that Thomas started this educational course. He said at the very beginning that the spatial distribution of the electric fields should be the starting point of your analysis and not the end point. He just said at the end, but the starting point, and that is what I want to go to a little bit more detail with my presentation. I want to show you possibilities to use this spatial distribution, the information of the spatial distribution of the electric field, to analyze multi-channel evoked potentials and multi-channel spontaneous EEG. That's too fast here. You all probably know, and that's why you are probably here, you know how traditionally evoked potentials, and that's the first part I want to talk about, evoked potentials or event-related potentials, how they are usually conventionally analyzed. You have, for example, two different conditions as they are shown here. You have frequent and a rare stimulus in this example. You record the EEG from a certain electrode against a certain reference. You average separately the EEG for the two types of stimuli, and you get this averaged evoked responses in blue for one type of the stimuli, for the frequent stimuli, and in red for, in this case, the rare stimuli. And then what you usually do, what usually has been done, and still is been done, is that you look at the amplitude differences between the two conditions at certain latencies. In this case, you find this beautiful P300 component as the difference between the rare and the frequent stimuli. I don't know where the laser pointer is here. Here we go. Here we go. So this P300 component, that's a way of analysis of evoked potentials as it has been done, but nowadays, you know, all of you, and you will see many companies in this meeting that show you that we can record EEG from many channels simultaneously. We can have this high-density EEG recordings here, in this case from 256 channels simultaneously recorded, covering the whole surface of the brain. The question is how to analyze this type of evoked potentials. Do you do the same thing as we have done with the single-channel recordings? Do we just select one electrode out of this 256, the one that we think is the most important for looking at the difference between conditions that we have been imposing to the subjects, and then do the same thing, namely measure amplitude and latency differences between conditions for this one selected electrodes? That's, of course, obviously not a very intelligent strategy if you have been recording for 256 electrodes and you just select one. Another way to do that a little bit more globally, and it has been done already 20 years ago and is still used in several applications, is to go a little bit more general by doing t-tests for each electrode and for each time point, and look at differences between conditions across subjects for each time point and for each of these electrodes. This is one possibility here in a study done about 20 years ago. This is another one a little bit later with more electrodes. The idea is you have each time point a t-test in the different electrodes, and you look at the ones that are the latencies where you have differences between conditions. That's a more global way. It is a bit dangerous because you have a lot of t-tests to do here. You have a lot of time points, a lot of electrodes, so you have to correct for this multiple testing in one way or the other. But there are other problems with this type of analysis, and one important problem Thomas already mentioned is the reference dependency of this type of analysis. The EEG, as you know, as Thomas explained to you, is a measure of differences between two electrodes, normally the difference between the active, what you call active electrodes, and the reference electrode. And this is the t-test, time point by time point, electrode by electrode t-test result that I just showed you before, measured against one reference, a frontal reference in this case. But unfortunately now if you change the reference, for example, against the average reference, everything changes. The latencies changes, the electrodes that were different is changing, and the whole topography is changing. So you have a problem here by this type of analysis, and this has to be avoided, because otherwise we cannot compare between different studies of different people, of different groups who use different type of references. And just using the same reference in order to be comparable between studies is not really the solution to that. So we have to have reference-independent measures. Another problem with this type of analysis that I just said that has been done up to now by measuring just amplitude differences between electrodes is that there is no direct relation between the potential maximum, where you saw maybe the maximum of your peak of the component, let's say the P300 component, and the sources in the brain. So to just select the electrode that had maximum amplitude and think that is the one we have to analyze and compare between conditions doesn't make a lot of sense when you want to go to make interpretation about where it came from. There is no direct relation, as Thomas said, depending on the orientation, because our brain has convolutions depending on the orientation of the dipoles. The maximum can be at completely different places on the scalp surface. This is shown here in this little example here. This is an auditory evoked potential. You see here the map topography that comes up at around 100 milliseconds because of the orientation of the dipoles in the auditory cortex pointing to the vertex of the brain, making an electric field that is maximal negativity in this case on the CZ electrode. But of course the source was not up here on the vertex. The sources were in the temporal lobe, in both temporal lobes on both sides. And only through inverse solutions, through source localizations that you will hear about this afternoon, you might be able to disentangle that and to get back to the sources where they have been. But the interpretation could be very easily wrong here by assuming that where the maximum is, you have had the sources in the brain. So what I want to show you, the way of analysis that I want to explain to you today is going directly to the electric field that has been produced by the momentary activity in the brain, to the electric field, and use these electric fields as the basis of your analysis. That's the starting point, as Thomas said. And from here, we go on and try to look for differences between conditions or differences between different subject populations. So this is the starting point of our data, the evoked potential maps. This is the nose, left ear, right ear. Red is positive potential, blue is negative potential, so seen from top, from 0 to 500 milliseconds in this case. Not every map is shown here. There's no space on this slide, but this is the data that you have in your hands. And with this, we are going to work. Not with this here, not with the waveforms, not with amplitudes. This is what we are going to work with. And if you look at that already here, just visually, these evoked potentials, you see right away what you have also as a definition of an evoked potential component is a stability of the field topographies. You see periods, and I try to illustrate that a little bit by animation, I think, if it still works. Yes. You see periods where these fields, the topography, the distribution of positivity and negativity remains relatively stable. So you have a certain number of periods of stability of stable maps. And what has been proposed several years ago is to use this observation and quantify this. Quantify this by doing what we proposed is a k-means cluster analysis with cross-validation to select the optimal number of clusters of an evoked potential. You have here the evoked potential overlapped waveforms of 256 recordings in a certain condition. You have the maps here, the series of maps across time. And now we apply this k-means cluster analysis to this series of maps to define the most dominant or the optimal number of maps that describe these evoked potentials. In this case, you have 1, 2, 3, 4, 5, 6, 7 maps that optimally describe all the maps that you had around in these 500 milliseconds, and then we fit them back to the data and label the different time periods, different segments, if you want, different periods with the corresponding map. So we have reduced this map series to 1, 2, 3, 4, 5, 6, 7 periods, 7 components if you want, but components not defined by a peak in the evoked potential, but defined by a period of stability of a certain map configuration. This is the application of this k-means cluster analysis to 2 conditions, in this case to this frequent and rare stimuli that I showed you in the beginning. Now, in top, the frequent stimuli evoked potential is the global field power curve, and in color labeled the different segments, the different map topographies, if you want. for the frequent and for the rare stimuli, and you see right away that there is a period here where the two conditions clearly differ. They differ in terms of amplitude of maps, of global field power, but mainly they differ in terms of configuration of the maps. There is a new map coming up, this P300 map, with a very particular configuration, with a maximum over the vertex that you don't see at all in the frequent stimuli. And it's not only the P300, even the one before seems to be different between the rare and the frequent stimuli. All the other periods seem to evoke the same type of maps, more or less. Let's say. So you have identified a period, a latency if you want, where different maps are present, and different maps by physics. Different maps means different configuration of the generators in the brain. Now you can go one step further. You do that to the grand mean evoked potentials across subjects. You take these maps and you fit them back to each individual subject. And you look which map is present in each subject, and that's what I try to illustrate here. You have this map series, you have the cluster maps, and you fit them back to the data, and you label the periods where these maps were most dominantly present. And once done so, you can define different type of parameters across subjects. You can define the onset of each of these maps, you can define the offset of each of these maps. You can define the global explained myriads that each map has. How much is the map present in this data? You can define the time of presence, the duration of each of these maps in the different conditions for each individual subject. That means what you can do is statistical analysis. Sorry, to go back again, statistical analysis, and compare these different parameters between the different conditions and find out finally whether one of these maps is present in one condition only, significantly present in one condition, and not in the other. Now, Thomas was talking about the advantages of topographic analysis, and one of the most important advantages is that they are reference independent. And he showed already a picture, and I just show it again here. You see the evoked potential, or an EEG map if you want, measured against different references, against the left mastoid, against FZ, against POZ, and against the average reference, and you see different colors. But if you ignore the color for a moment and you only take the equipotential lines, which is shown in the second line, you see that they are not different. The topography remains the same. It's only the level from where you look at them that changes. It's like looking on a landscape from the lake level. All mountains are above you, or you are on the top of the mountain, everything is below you, but the topography, the landscape does not change. You just changed your position to look at them, but you don't change the reference. So maps, topographies, electrical fields are reference independent, while, as I showed in the beginning, measurements of amplitude and latencies are not. The second advantage is, as I tried to say before, is that EEG maps are the precursor for source localization. We will hear this afternoon about source imaging, source localization based on the electric fields, on the topographies of the electric fields. The more electrodes, the better coverage you have, the better your source localization estimation will be. So they are directly related to the sources in the brain. It's a linear relation between the two of them, including a source model that you use and hopefully a relatively good and individual head model. So looking at maps directly means that you, in principle, look at the precursors of sources. And as I said before, the different, and that's the important advantage, if we only look at and we try to identify periods or moments or conditions where maps differ, we directly can claim that we have differences of the source configurations in the brain, even if you don't say where they come from, but we are sure that physically the total configuration of the sources in the brain have changed between these two conditions because the maps on the surface were different. I'm going to finish this evoked potential part with an example, just to show you the sort of comprehensive analysis of evoked potential as we would propose it, not only we, several papers have been proposing that over the years. This is an example a bit related to what Thomas said, a semantic decision task where you have pairs of words. They are either semantically related or not. The subjects have to say whether they belong to the same semantic category or not, just by pressing a button. We get, in the behavioral response, we get this famous priming effect with a much faster reaction time to related than to unrelated words, and would like to know where in the brain or why this happens, what happens in the brain in order to be faster to one condition than to the other. This is the analysis of the evoked potentials across subjects that has been done here. First, the t-test, as I showed you in the beginning, the t-test for each electrode at each time point. On the top, you have, this is time. Here, these are the different electrodes, and in red are the t-values. So you see, you can identify two periods, one at around 150 milliseconds or so, and a big one period around 400 milliseconds, where you have a lot of differences between related and unrelated words. More in the bottom here is a test of the global field strength. It's just a one measure test. It's not for each electrode, but it's for the global field power of the whole electric field. You just test strength differences, and you see a little difference here. But this one is the most important, which is the randomization test that Thomas was talking about, the test between testing for differences of map topographies between the two conditions independent of strength. And that's really where you can identify whether different things have been going on in the brain or not, whether different configurations of generators have been present between the two conditions. And yes, you can identify two periods, one around 150 milliseconds and another one around 400 milliseconds, where apparently different topographies appeared. That's nice, that's beginning, but now the next step would be to do this microstate or this segmentation, this k-means cluster analysis. And what you see here is that these are the two conditions again. These are the unrelated words, the related words. This is the global field power. And in color, again, coded the segments with the different maps. Sorry, the different maps identified by the k-means cluster analysis. And what you see is that in the first period, you do not really have different map topographies. Even so, this one assumed or suggested that you have different topographies, but no, it's not the case. You have the same topography. What you have is a change in the duration, in the presence of this map, making then a period where this condition already is in, let's say, the brown map here, while this one is still remaining in the red one. So that's a very crucial information that is completely different than saying, we have different things that happened in the brain. No, it's not the case here. It's a different duration of the same process that makes a shift from one condition to the other, which is, I think, an interesting new information. But the second period, this huge one here at around 400 milliseconds, is clearly, nicely identified as a new, as a unique segment, a unique component, a unique map topography for the unrelated words against the related words. Then you can, as I said, fit this information back to each subject, look for statistical differences between them, and then you clearly can identify, in this case, a first time period with differences in presence of the map, this red one here, and the second time period with difference in presence of this map in yellow here. This second period is the clear N400 component here, proposed by source localization to be generated in the temporal lobe, while this one here in the early component, around 120 milliseconds, 140 milliseconds, seems to be, at least in this estimation, be localized in the left occipital area, in the area of the visual word form, in the visual word form area. Okay, that was an example just to illustrate a way of spatial analysis of evoked potentials that can be done by base your analysis, by using the spatial information as the basis of your analysis. And now let's get to spontaneous EEG. Also spontaneous EEG you can record, of course, now with high density EEG, with this case 256 channel, spontaneous activity, eyes closed activity. You easily identify periods of increased alpha activity. That is typically observed when you close your eyes. The standard analysis, again here, what you see in the literature normally is, oh, sorry, that was too fast, is that you select certain channels and you look at oscillations of these channels across time. You look at oscillations, you look at the frequency of oscillation, you look at the amplitude of certain frequencies of these oscillations. And you do a variety of frequency analysis, and I'm sure others will more talk about this type of analysis today in this educational course. You can do a simple spectral analysis using an FFT. You can do envelope analysis, looking at certain frequency or frequency bands, amplitude across time. You can do time frequency analysis with more or less temporal resolution. Here is time, here is frequency, and in red is the power. Or you can select 2 channels or more channels and do a type of coherence analysis, do correlations between different waveforms, maybe look at phase lags, and maybe look at connectivities. But this is all based on frequency analysis, on analysis of oscillations of certain electrodes. And what I want to show here again is to base it on spatial analysis of the electric fields and not on this. EEG not considered as an oscilloscope, but EEG considered as an imaging method, looking at the momentary activation, global activation of the neural generators in the brain. That's what I try to illustrate here. So instead of looking at oscillations, we assume that EEG, or we say that EEG at each moment in time looks at the global activity in the brain, projected on the surface, measured with high-density EEG or multi-channel EEG, and then constructed as potential map, as electric field. And then what we do, exactly as in evoked potentials, we look at the evolution of these topographies, of these electric fields across time, but now not evoked, but spontaneous. And when you do that, and here is just an example of a spontaneous EEG for 20 seconds, and you see some of these maps across time, not a lot, because there's no space here, just a few of them, and that's what we are working here with. Like with the evoked potentials, this is our basis, this is where we work with. And when you look at them, you see maybe not a lot of structure, you are a little bit surprised of what we could do with that, but if you look a little more carefully, you will see that there are maps that appear again and again with the same configurations, here marked in red or in blue. And what you have is a temporal dynamics, a temporal evolution of these maps across time. But the configurations of these maps are not random. There are similar configurations that come up and up and up again. And in addition, sorry, I have to go back. In addition, you see periods where, again, like in evoked potentials, these topographies seem to be stable. The only thing that changes is the polarity, because we are not evoked potentials. We have now a spontaneous activity. The polarity is changing, but the topography, the distribution, seems to be stable for certain periods of time. And that I want to illustrate a little bit more in detail here. Here I have selected only a 2-second EEG, and here are all maps selected at the global field power peaks, here marked in blue, one after the other. And you might see that there seems to be periods where the topography is the same, it just changes red, blue, blue, red, red, blue, blue, red, red, blue, blue, red. And these changes in topography is due to the neuroelectrical oscillations that are due to the excitability, the continuous excitability and inhibition of the neural ensembles at a certain area in the brain. So this activation, inhibition repeatedly causes these oscillations in the brain, and these oscillations then on the surface, as Thomas has shown, cause the changes, polarity changes of the dipoles, and through that polarity changes of the maps without changing the configuration. And what I do here is maybe not really something that people like to do who look at oscillations, but what I do, I completely ignore these oscillations. I don't care. And I don't care means that I now change the polarity of each second of these maps, and you have seen that. That was too fast. I have now ignored the blue, red, red, blue, blue, red. I change the polarity of each second one, and then you see very clearly the stable periods that appear in the spontaneous EEG, stable periods of topographies that last for about between 80 and maybe 150 milliseconds. So, sorry to go back. So what we propose to do, or what has been proposed over more than 40 years now to do, is to segment the spontaneous EEG in periods of stable map topographies, of periods of time periods where the topography does not change except of inversion of polarity. This has been proposed in the 70s already by Dietrich Lehmann, so more than 40 years ago. He already observed that in a very primitive way, in quotes, but he already observed that if you look over time, just at the location of the maximum and the negative of your maps, you observe the stabilities of the fields. And he claimed already there, then, at that time, that the spatial stationary segments might be the basic building blocks of information processing, possibly reflecting the time for consciousness. That was an idea that he formulated before having possibilities to really go into detail of proving this concept or this idea. So what we propose to do in the 90s is to use exactly the same as for the evoked potentials, namely a k-means cluster analysis, using cross-validation to determine the optimal number of maps, but now to describe your spontaneous EEG, to describe all these maps, which are the most dominant topographies that are present in this spontaneous activity. And what we have shown, many groups have shown across time, is that most often we end up with four maps, four main configurations that explain around 70 to 80% of the variance in your data. Each of you, if I record an EEG, spontaneous EEG from each of you now here in this room and I ask you to close your eyes, most of you will produce these four maps, and these four maps will explain about 40% of your variance. But the point is that the temporal evolution of these maps, the way they follow each other, the lengths of each of these maps are different between you and your neighbor. And that makes you having a different thought than the neighbor has at this very moment in time. Here are different studies from the 80s, 90s, 2000, 2010, 2014, up to now, different studies with different subjects, different type of subjects, even some clinical studies. You see that most of them show these four prototypical maps that Dietrich Lehmann showed many years ago, with a left-right, right-left, anterior-posterior, and a more central configuration. It comes up again and again and again in your data. 4 seems to be not a lot, but 4 can have, in terms of temporal organization, a lot of variance and a lot of variability and a lot of uniqueness between you. So what we do then, what has been proposed to do then for statistical analysis, is to do the same as for the evoked potentials, namely fit these maps back to your data, doing a spatial correlation and label each time point with the map that is best correlated with. This could be now result in a random distribution of labeling, of attributions, but no, it doesn't. What you see is that there are always periods, and this is now really data-driven. This has no assumption behind it, data-driven, that each period is mainly represented by one of these maps. It's not a random distribution, it's really segments of stable configurations, what have been called the so-called microstates. And then you can define different types of variables for each of these states, if you want, namely duration, the explained variance, the percentage of time that each of these maps is present. You can look at transition probabilities between maps. You can look at complex things like fractality indexes, here the Hurst exponent that has been proposed in some studies. And there are different parameters that you can define that define the presence, the temporal dynamics of these 4 microstates, these 4 maps. This is a study that has been recently finished, not yet published, come from our group, is where we looked at all data that we have recorded over the last 10 years or more with high-density EEG, 256 channels in different age ranges, and we looked at developments across lifespan of these 4 microstates, if you want. And we again ended up with these 182 subjects, ended up with these 4 prototypical maps, using a k-means cluster analysis, explaining again around 80% of the variance in all these subjects. We have from newborns up to 87 years of age, and we looked at the development of the duration of these maps across the different time or age periods. Sorry, we looked also at the occurrence of these maps, how much they are present per second across different age groups. And what you see for the duration is you see that one of these maps, this class number C, which is this map here, seems to increase in duration when you get older. The others seem to be more or less stable. There is a period during adolescence where this map here, which is class B, which is this map here, seems to be less present than the other ones. For the occurrence, the same here during adolescence, there seems to be quite a dip of one of these maps. Not of the others, but of one of these maps. There seems to be a decrease of some others. But here is a clear period of life where you see massive differences between the different microstates. Of course, also in newborns, there is a massive difference with nearly equal distribution of the 4 states that you don't see afterwards anymore. Interesting was also to see the difference between female and male in this collective of people, in these 180 people. And what we see that is during adulthood, there's a difference in this class C microstate between females and males, with much more presence of this class microstate, of this microstate in females than in males, between about 20 and 60 years of age. On the other hand, there is more presence of this class D microstates in males than in females during this age range. So there seems to be a difference between male and female for these two types of microstates, and you will see later that these two microstates are also interesting in different pathologies. So, as I said, it has been proposed that these different microstates of the brain, that these different map topographies implement different conscious, reportable mind states, that they represent something like the atoms of thought in your continuous, spontaneous activity. That these microstates are the electrophysiological correlate of conscious integration at the whole brain scale, global level. So if these EEG microstates reflect a continuous stream of thoughts, then one would assume that microstates parameters, that's the one as I proposed there, could be defined like duration, explained variance, and so on, transition between microstates. The temporal dynamics of this structure changes when the quality of your mentation changes. For example, when you are just born, when you are in sleep, when you are under anesthesia or in coma, and of course in different psychiatric diseases with different mental disturbances. And some studies I want to show, I cannot show all of them, but one of the study here from a group in Frankfurt in Germany, Helmut Laufs and his colleagues, they looked at EEG resting states in sleep, in the different sleep stages. Here sleep stage awake and then sleep states 1, 2, 3. And again, they found these 4 microstates, they do not seem to change in topographies. The topographies seem to stay the same in different sleep stages. What changes is the duration, the temporal dynamics again. And you see that all of them increase in duration drastically when you go deeper in sleep. So you stay longer in the microstates. You don't change the configuration, you stay longer in them. This is a study using recording subjects on the different levels of anesthesia with propofol anesthesia applications, and you see that again across subjects, these are different subjects going in anesthesia, again different subjects, different doses of propofol, having again the same, more or less same microstate. So the microstate topographies, spatial configuration again does not change, not drastically change, but what changes again are the temporal dynamics. In this case, you do not increase, like in sleep, the microstate duration, but you decrease the duration in all of them. All of them showed a significant decrease in correlation. So anesthesia, going to anesthesia does not mean the same as going to sleep, which is obvious, but is here defined with one of these parameters. And finally, the disturbances of these microstates in different psychiatric diseases. And here I have many, many studies from different groups at different places have looked at psychiatric or neurologic diseases, for most of them in schizophrenia, but also in depression, Alzheimer's disease, panic disorders, some of them also at schizophrenias that are only at risk to develop schizophrenia, and so on. I cannot go in details, but what all of these studies, most of these studies showed is a difference in the temporal dynamics of microstates, not in spatial configuration again, mainly differences in duration, mainly difference in duration of these two last microstates, microstate C and microstate D. I'll show you only one example to end with, which is a study where we looked at the microstates in a group of population that have a genetic malformation, the 22q11 deletion syndrome, which makes them much more vulnerable to develop schizophrenia when they are adults than normal subjects. About 30% of them develop schizophrenia when they are adult. We measured them when they were adolescents, so they were not yet schizophrenic at all. But what we found is that there were clear differences in duration between these subjects against their age-matched controls for microstates C and D, with C being much longer present in this population, in this genetic population than in the controls, and microstate D being less present. We then did exactly the same analysis with a group of schizophrenic patients, adult schizophrenic patients, and found the same thing. Found again an increase in microstate C and a decrease in microstate D, which would then indicate, on the other hand, that maybe this is a sort of a biomarker, a predictor of those subjects who might develop schizophrenia when they are adult. We are doing a longitudinal study to see whether this will be true, to look at them again and again and again, and then identify those that unfortunately for them became schizophrenic, and look whether they were the ones that already had this increased microstate C before they became schizophrenic. We also found differences in the transition between the different microstates using some Markov chain analysis, and you see also here that there are differences between these 22q11 deletion syndrome patients and controls, namely a much more often transition from A to C or from B to C. That's marked here in red. Just one word for source imaging. I will not go into details because there are different courses that are going to talk about that. But as Thomas already said, we can estimate the sources in the brain. It's a different way of looking at the data. We can estimate the sources in the brain that produced the map at each moment in time that we measure on the surface. As more density electrodes, more number of electrodes and better distribution of electrodes we have, the better this estimation. And we can look at the development of the activity in the brain space across time. But I don't go in detail here, this will be explained much more. I just wanted to show two examples of localizing now this EEG spontaneous microstates using the type of source localization. Where do these microstates come from? What are the generators? What are the networks in the brain that generated these microstates on the surface? And this is a study recently published from Roberto Pascual Marquis, where he estimated that by using individual source-based analysis and then statistics across subjects, 109 subjects analyzed here with 61 electrode recordings, and he proposed these microstates as being generated in the occipital lobe for the first one, the second one also more a visual one, the third one being more generated by frontal sources, shown here, and the fourth one, by parietal posterior cingulate activities. That's one way to go. Another way to go is to do a sort of an analysis as it is used in fMRI analysis, and I want to just go through that type of analysis with you for a second, which is take your EEG, spontaneous EEG, do this sort of feature extraction by K-means cluster analysis, define your states, your microstates in our case, look at the time course of these microstates across time by just fitting them back to the data and calculate correlation. But also do inverse solution for each of these maps. Then you have the estimated activity for each voxel in the brain. You can look at the time course of them. And then you can do a general linear model correlating each of these time courses with these time courses and look which of the voxels in the brain correlate with the activity of your microstate on the surface, and you identify then statistically the significant correlations, the voxels in the brain that significantly correlate with this time course. And doing that, you get to a different type of estimation of these microstates. We then identified in these 160 subjects from the pool that I presented you before with 257 electrode recordings, we identified the first one as being generated in the visual cortex, the second one more visual and parietal temporal, if you want, the third one very clearly anterior cingulate frontal activity, and the third one being more frontoparietal distribution rather on the left side. And interestingly, they quite nicely correlate with functional MRI resting states. And you will, if you have time, you can see the poster of Anna Cusso presented on Monday, very nicely correlate with fMRI resting states. And we did a simultaneous EEG fMRI and a study that she will present on her poster, showing that each of these microstates is related to a certain fMRI resting state. I want to stop with that and just go to the conclusion. I'm sorry for that. But this is analysis you can see on the poster of Anna Custo. I want to finish with the conclusion that the temporal, do I make it? That the temporal progression as a first conclusion of the brain electric activity can, as I showed you, this be described as sequence of segments, of short-lasting periods of stable scalp map topographies, being it in evoked potentials or in spontaneous EEG. Reduction of the EEG in the state, in the topographic, in terms of topographic distributions. The topography of these maps are reference independent. That's a very important message, I think, because that's not the case, not for frequency analysis in spontaneous EEG and not for amplitude analysis in the evoked potential. Frequency analysis, correlations, coherences are all extremely reference dependent if you stay on the signal space. Spatial configuration changes of the scalp potential maps, as I showed you, directly reflect changes in the source distribution in the brain. So it's a precursor of source localization. The temporal structures of microstate describes, that's what we claim, what Dietrich Lehmann claimed, the ongoing mental activity. And the mental diseases, different mental diseases, especially schizophrenia, as I showed you, and cognitive dysfunctions are characterized by abnormal temporal structure, not spatial structure, abnormal temporal structures of the spontaneous or the evoked microstates. I want to finish with that, and I thank you for your attention. Is there a question? Yes, please.
Thank you so much. Very, very nice talk and wonderful results, especially for the resting state. I'm fan of CAR-tool also for the tool. My first question is about, is there any constraint about the temporal length of the window to choose?
No, not at all. There is a little bit of smoothing if you want to do. You don't have to, but we do a little bit of smoothing to reduce the noise if you want.
If the microstate, the EEG microstate, they reflect some underlying cognitive activity, it should be maybe at least related to this activity.
Indeed, yes, indeed, absolutely. I prefer to do that data-driven and not hypothesis-driven. And yeah, that's one example that I tried exactly to show this, is that, you know, that one can remain longer than the other one in a given condition because the cognitive activity or the task that you have to do demands that this type of processing, like there in the visual word form area, lasts a bit longer because you didn't, that's an interpretation, or because you didn't prepare for this word. So you are searching a bit longer in this type of, in this period of activity, yes.
Okay. My second question is about the application of the sources. Just to understand, so you reconstruct the dynamics of the sources and you apply the same procedure or not? It's possible to do that instead of applying all the k-means and the clustering on the scalp EEG. We can reconstruct the dynamics of the sources and then applying it for it because we have it at, I mean, the same temporal resolution finding.
Yes, the same analysis in source space. That's what you're asking, I think.
Yes.
And yes. Yeah, we are working on that. I know other groups that are working on that. there is it's not easy because it's a dipole, it has different orientations, so it's a vector that you have working with, not the current density that makes it complicated. You have 5,000 or more voxels if you want in the brain. It should give the same thing, given that all is linear, as Thomas said. It should finally end up in the same thing, but it's a bit complicated to do calculus-wise, but should end up in the same. But yeah, we are working.
I have a third question. Because we adopted the same procedure, but for the EEG connectivity maps, like yes. searching from functional connectivity state in the EEG scalp. And what do you think about the k-means? Is there any way to use another clustering or to improve about all this question and assumption of the k-means clustering?
Yeah, yes, we have in the free available software, we propose also other methods than k-means and also different type of k-means. Yeah, the results are a bit different, but they're not as drastic as you would expect. So the k-means for me had the least assumptions, less than an ICA, but Scott will talk about that for sure. Less than ICA or PCAs or other type of analyses that try to separate different states. We didn't really evaluate that properly, but yeah, the k-means is one of them. Yeah. Please.
It's wonderful. So I noticed that you mentioned across a number of studies, 4 major mechanisms are mostly focused on, and we know we're trying to relate to a number of resonance networks, and from
yes.
fMRI and other literature, of course, there's more than 4 there. So do you see actually 4 is a good representation from each data, or do you think there's room we should try to push that to kind of get more information from that?
Yes, yeah, you're of course right. 4 is it's not all. fMRI resting states show more. I think I have a slide here, that's why I'm going back. We have started to, you see, I jumped this slide, I think. This analysis that you can see in the poster of Anna Kusto, we have identified 8 microstates, and not only 4 with this data set. The first 4 are still the same as the ones we have seen in all the different data with different number of electrodes, explain about 70 to 80% of the variance, as I say. There are 20 to 30% missing, that we find most of it with these 4 additional ones here. Yes, you have more. Now, the question is whether this additional 20% that you explain will be the ones that you search for differentiating your populations or your clinical cohort. I don't know. I mean, we are happy to try to understand the 4 we have and the temporal dynamics of the 4. Everything gets more complicated if you add the other 20%. Is the 20% extremely relevant or not? I cannot tell you. But yes, there are more. There are definitely more available. Yes. Okay, so we go to Scott is the next. Yes. Okay. To Scott McCaig, who will continue hopefully in the same way as we started.